The properties of an atom depend on the pull of the electrons towards the nucleus of that atom, which originates from the interaction of positive and negative charges. The nuclear charge, or Z, of an atom is the number of protons within the nucleus, the same as the atomic number. Each proton contains a positive charge and will attract the negative charge of a surrounding electron. The outermost electrons of an atom, or valence electrons, are pulled by the nucleus, but we must also consider the effect that other electrons will have on the pull. The repulsive forces between the negative charges on the electrons will decrease the pull felt by each electron from the nucleus. This repulsion is called electron shielding, and the pull that is felt is called the effective nuclear charge, or Z effective. The simplest atom, hydrogen, with its one proton in the nucleus and one electron in the 1s orbital, is the only atom where the nuclear charge and the effective nuclear charge are the same, since there are no other electrons to repel hydrogen's one electron. However, the shielding effect begins as soon as another electron is present in the atom's orbital and repulsive forces between the negative charges take effect. Let's take a look at helium. The nuclear charge of helium is 2. However, the effective nuclear charge is about 1.7. The electrons are both residing in the 1s orbital and will slightly repel one another, which will decrease the pull felt by each electron. Now let's take a look at lithium. A neutral lithium atom has 3 protons and 3 electrons. The valence electron is in the 2s subshell. However, the other 2 electrons are in the 1s shell. These are what we call the core electrons. The core electrons are in the completed shells closer to the nucleus than the valence electrons, while the electrons within the same shell will shield one another with repulsive forces. The core electrons exhibit shielding on the valence electrons as well. So lithium, with a nuclear charge of 3, will have an effective nuclear charge of about 1.3. This can be estimated by the formula Z effective is equal to the nuclear charge minus the shielding constant, this lowercase sigma. The shielding constant accounts for the repulsion coming from the core electrons as well as electrons residing in the same shell. The more core electrons there are, the stronger the shielding and the higher the shielding constant. Now let's take a look at the periodic table. As we move across a period, the nuclear charge will increase, but the number of electrons will also increase. If we look at beryllium, the nuclear charge is 4, but now there are 2 electrons in the valence shell. This results in more electron repulsion, and the effective nuclear charge is around 1.9. It is important to note here that while the effective nuclear charge is not 1 unit higher than the lithium atom, it is still more. Another way to state this is to say that another proton within the nucleus will have a stronger pull on that valence electron than another electron in the valence shell will repel that valence electron. This trend continues across the periodic table. It is also important to observe how the effective nuclear charge is affected as one moves down a group on the periodic table. While the number of protons is increasing, the number of completed shells is also increasing. Because the inner electrons shield the outer electrons most effectively, as the number of core electrons increases, the pull from the nucleus felt on the outermost electrons decreases.